Okay, so the last chapter we covered was chapter 10, which was inference from two samples. And I've decided to skip chapter 11 and do it later because first we looked at one sample against a hypothesized mean, and then we compared two samples, two independent samples, and then two paired samples. And so it makes sense to me more to go on to the next phase, which would be comparing three or more samples. We'll come back to correlation and regression at a later time. And it just doesn't make sense to move on to non-parametric statistics before we finish this up. So we're going to do chapter 12, which is analysis of variance. Okay, let's think back to the flow chart that I showed you before. So if we think about our research question and we want to just describe a sample, we would use descriptive statistics. If we want to compare, we have to consider the number of groups we have. If we have one group, we do a one sample t-test against a hypothesized mean. If we have two groups, we need to consider, are they paired? If they're not, then they're independent, and therefore we do an independent samples t-test. If they are paired, then we would do a paired samples t-test. Now we can consider three or more groups, but the first thing we have to consider is how many independent variables do we have. If we have one independent variable, we would just do a one-way ANOVA. If we have two or more, we would do what's called a factorial ANOVA. And again, we'll come back to this later. So an overview of analysis of variance. ANOVA comes from ANOVA, which is an acronym for the analysis of variance, which is referred to it as ANOVA. It's a hypothesis testing procedure that is used to evaluate mean differences between two or more treatments or populations. As with all inferential procedures, ANOVA uses sample data as the basis for drawing general conclusions about populations. The major advantage of ANOVA is that it can be used to compare two or more treatments. When we do an ANOVA, we're now moving away from T distributions, and we are now looking at an F distribution. You might remember that the Levine's test had what I showed you was an F statistic. It followed an F distribution. There is a different distribution for each different pair of degrees of freedom for the numerator and denominator, because an F distribution is a ratio of variances. The variances for the numerator or the numerator variation divided by the denominator variation, and I'll talk a little bit more about that. So because of this, because it is a ratio, the values can't be negative, and the exact shape of it depends on the two different degrees of freedom, but you'll see that it is a right-skewed distribution, and it's not symmetric. So one-way analysis of variance, or one-way ANOVA. So if you've watched the Khan Academy's videos, you'll recognize that we have three groups, and you have variation within the group, and then we also have variation among the group, and that's what ANOVA is testing. And so the ratio is the variation between divided by the variation within. And I'll talk more about that in a minute. So the statistical hypotheses for ANOVA is, in general, the null hypothesis states that there is no treatment effect. In an ANOVA with three groups, the null could appear as the mean of the first group is equal to the mean of the second group, which is equal to the mean of the third group. The alternative hypothesis states that the population means are not all the same. So you could see it with the not equal sign, or you could see it written out as there is at least one mean difference. The test statistic, like I said before, is an F test, and the F statistic is figured out by taking the variation between samples divided by the variance within the samples, and therefore you get the degrees of freedom for the numerator and the degrees of freedom for the denominator. Now there's different terminology in analysis of variance, and you've seen this already in SPSS. In ANOVA, the independent variable that designates the group being compared is called a factor, and the individual conditions or values that make up a factor are called the levels of the factor. So if we're looking at regions, north, south, east, and west, there are 4 regions. So if my factor is a region, there are 4 levels of that region. Again, if I'm looking at gender, I would have 2 levels of gender. A study that combines 2 factors is called a 2-factor design or factorial design, which we'll do later on in this presentation. Okay, as with all inferential statistics, there are assumptions of ANOVA that need to be met. The first is that each group sample is drawn from a normally distributed population. All populations have common variance, which we'll test with the Levine's test. All samples are drawn independently of each other, and within each sample, the observations are sampled randomly and independently of each other. So why ANOVA and not a bunch of t-tests? As we increase the number of t-tests, we increase the risk of making a type 1 error. Remember those? Those are the mistakes we make when we say the null hypothesis is false when it is not. It is the incorrect rejection of a true null hypothesis, otherwise known as a false positive. Just think back to that slide with the picture of the pregnant man. That's a false positive. So in the Khan Academy, you saw him calculate the sum of squares between and the sum of squares within. When you look at the output in SPSS, you will see an ANOVA source table. And we have the sum of squares, the degrees of freedom, the mean square, and then the F statistic. And just briefly, all we need to look at is the significance in the ANOVA source table, and then our F statistic, and the degrees of freedom. But I'm going to show you where they come from. So K is the number of groups. So if you think back to the slides with the circles, we had 3 circles. So 3 minus 1 would be 2. So the degrees of freedom for the numerator is 2. Now, I don't remember exactly how many we had in our sample size, but N is the overall sample size. So let's just say it was 30. So 30 minus K, which was the number of groups we had. So 30 minus K would be 27. So we'd have 2, 27. And then we would divide this value, this divided by this, gives us the mean square. This divided by this gives us the mean square between, and this gives us the mean square within. We divide these two values, and that gives us our F statistic. Then we would go look it up in a table, and we'd have to look at the numerator degrees of freedom, the denominator degrees of freedom, find our critical value, and then see if this F statistic is greater than that. Well, we're just going to use the p-value, which is a whole lot simpler. But that's what's going on in the ANOVA source table. So let's try one. Lead and IQ. This is on page 535, example 1. We see we have 3 levels of our factor. So we have a low, medium, and high blood level of these number of individuals. And then this is the IQ for each one of these people. Okay, so we enter our data into SPSS. So instead of doing it in chunks like this, I would put all these IQs, just like I did with the independent samples t-test, all of them in one long column, and I would label this person 1, 1, 1, 1, 1, all the way through. I'd label this person 2, 2, 2, 2, 2, 2, 2, all the way through, and 3, and then I would go and value label low blood level, medium blood level, high blood level, which is what I've done here. Okay, so we've entered our data. Before we do anything else, let's check and see if we have normality. And we remember how to do this. We go to Analyze, Descriptive Statistics, Explore. So we would go move our IQ over and our lead level over, and we would just click plots. Plots. And then we click Normality Plots with Test, and we come and we look at our output, and we can see that for all levels of our independent variable, we are not significant. Therefore, we can say they're all normally distributed. All right, so just to kind of situate this in an actual research study, if this were something that we were doing, what would be our research question? We would want to know, is there a difference in IQ among children with low, medium, and high levels of lead in their blood? And if you were doing this in a project, you would have to say how you operationalized low, medium, and high. And just FYI, the data set is it's data set 8 on page 641. So here, this is what they're doing to operationalize their variables. So the data are from 121 subjects, and they show the first 5 rows there in the example. Data are measured from children in 2 consecutive years, and the children were living close to a lead smelter. Lead is blood level group. 1 is equal to low level. So this is for blood levels that were less than 40 micrograms per 100 milliliters in both years. So they're operationalizing what they're calling low, and then what they're calling medium and high. And then age is age in years, and sex is sex of subject. And year 1 is blood level in first year, year 2 is blood level in the second year, etc., etc. And IQ is the verb measured in the verbal IQ score, performance, and full. So this is important when you're actually doing your own research studies. You have to tell the reader what exactly it is you mean by your variables. It's called operationalizing your variables. Anyway, that's a side note. Okay, so the steps for hypothesis testing. First, we have to state the hypotheses. So the null is that the mean of the low group is the same as the mean of the medium group, which is the same as the mean of the high group. So I'm going to say in words, the null would be that there is no difference in IQ among the children with low, medium, and high levels of lead in their blood. Alternate is that there is at least one mean difference. Step 2 is we set the alpha level at 0.05. Step 3 is we're going to calculate the test statistic. We're just going to check the significance level, and then we have to make the conclusion. All right, so we're going to do a one-way ANOVA. So we go to Analyze. We come down to Compare Means. We slide across and we come down to one-way ANOVA. When we do that, this box will pop up. The variables will be here. We're going to move IQ to our dependent variable, and then we're going to use or move lead level to our factor level. We have two things to check. We're going to check estimate effect size for overall test because I don't believe that's auto-checked. And we're also going to do the post hoc. And then we're going to come back and do options. Okay, so if we find that there is a significant difference, we will know that for the overall, or what we call the omnibus test, that there's significance, but we won't know where the differences are. Is it between Group A and Group B, Group A and Group C, or Group B and Group C? So what we do is we click the post hoc up here, which means after the fact in Latin, and we'll click Bonferroni. Before I had taught LSD, and both of these are fine. LSD is not the drug, it's least significant difference, but mostly what you see in the research is Bonferroni, so we're going to go over that one. Okay, so you click Bonferroni, and then you go back and you click Options, and we want to get descriptive statistics, homogeneity of variance, that's our Levene's, and then I want to just do the means plot to take a look at that. We click Continue, and we go back and we click OK. So in order to check the assumption of equal variances, we're running the Levene's. Remember that the null hypothesis for the Levene's test is always that the variances are equal, and the alternate is that they are not equal. So if we do not reject the null, then we have equal variances. So we want a significant value greater than 0.05. Okay, so first we see the descriptives, and here we have the means for the three groups. We can see that the low level has a much higher mean IQ, but is it significant? So we have 102, 94, and 94. Now, if you know anything about IQ, it's a normal curve, right? Or rather, normal curve. And at the peak in IQ, 100 is the absolute average, and it's usually plus or minus 15. So these guys are all within the normal range of IQ, but we want to know, is there a significant difference between them and among them? Okay, so we check Levene's, and we see that based on the mean, we have no significance, and therefore we have equal variances. So we want to evaluate our ANOVA table. We see the sum of squares, degrees of freedom, mean square. Here's our F statistic and our significance value. You can see that this is less than 0.05, therefore we have a significant omnibus or overall test. Our overall significance, our overall ANOVA is significant. There is a significant difference among the three groups, but where is the difference? So we chose Bonferroni, and we can see that if we compare low blood level to medium blood level, we slide across and we look and we see we don't have significance. We have low blood level with high blood level. We slide across and we also don't have significance. We have medium and high, and again we don't have significance. So then we think, well, what's going on? I don't understand. So what I did was I went back and I reran it with the least significant difference post hoc and a Bonferroni post hoc. And you can see that here now we do have significance between the low and the medium and the low and the high, but not between, let's see, medium and high. I should have had another arrow there. And then here with the Bonferroni, we don't have significance among any of these. And so what could be causing that? If you have a lack of statistical power, for example, when the groups have small sizes, or when pairwise comparison tests are not statistically powerful, it is less likely to detect significant differences. You may have a high number of factor levels, which could also be an explanation for this. The more pairwise comparisons you have, the more your p-values will get penalized in order to decrease the risk of rejecting the null if they are true. You may have a weakly significant global effect, and you might just be using a conservative multiple comparisons test. So this is kind of where you, the researcher, have to make the decision. if you see this, you might want to go back and try a different post hoc test. So say you have an overall significant F test, and then your pairwise comparisons are not significant, go try a different pairwise comparison. Anyway, just wanted to show you that. Okay, so let's go to our effect size. Before we used to have to calculate this. Now we can click that little check box and it will give us the point value, the point estimate, and we can see that 0.065 is our eta squared. The interpretation is, and this is the Greek letter eta and squared, so they've written it out this way. We could just write it in words. 0.01 is a small effect, 0.06 is a medium effect, so this is a medium effect, and 0.14 indicates a large effect. This is calculated by taking the sum of squares between here from the output and dividing it by the sum of squares total. You get the same exact thing, but the difference is in the interpretation. Before it was just this weird benchmark, the Cohen's d. You just have to go on faith that those are the benchmarks, but here what it stands for is that 6.4%, so if I move this over 2 places and get a decimal, 6.4% of the variance in the dependent variable, which was IQ, can be attributed to the independent variable, which was lead level in the blood. And then we can just look at the means plot. You have to be careful at looking at the units or at the values on the y-axis, because sometimes they're very small and it may overemphasize the distance here, but you can see that this was 1.25-ish, 1.3, and then 94, and so it seems like a substantial difference. It will just depend on which post hoc test you choose to use. Okay, so let's go to state the conclusion. We would state in words that there is a significant difference in IQ in children among the 3 levels of lead in the blood. And here it is in APA, and here it is in AMA. And because we're going to report the post hoc test that were significant, I'm going to say a least significant difference post hoc test was conducted, and it was determined that there is a significant difference between the low group and both the medium and high groups, but no difference between the medium and high group. And I have the ANOVA table here because you need that for the F goes here, the degrees of freedom 2 and 118 for the within group, and then your p-value, and then you get the eta squared from the previous slide. Okay, so let's do a two-way ANOVA, a factorial ANOVA. So what is it and why do we do it? The two-way ANOVA compares the mean differences between groups that have been split on 2 independent variables called factors. The primary purpose of a two-way ANOVA is to understand if there is an interaction between the 2 independent variables on the dependent variable. So let's look at an example from page 547. In this particular problem, we have 2 independent variables, gender and age. Gender is 2 levels, age is 3 levels. Age is a continuous variable, but they've made a continuous variable into a categorical variable, so it's got 3 levels, 18 to 29, 30 to 49, and 50 to 80. So we have a 2 by 3 factorial ANOVA. And our dependent variable is pulse rate, which is continuous. So an interaction effect is when the lines are far from parallel. Here we have female is the blue line and male is the red line. And you can see that these are not parallel, right? We have this kind of peak here in the male group. So when there's no interaction effect is when they are approximately parallel, which means that the different categories of the variable have the same effect across the different categories of the other variable. For this here, we do have an interaction effect, and I'll explain that. So for the assumptions are the same for a factorial ANOVA as they are for a one-way ANOVA. You have to have normality, you have to have equal variances, our friend the Levine's test. One thing about normality, each cell comes from a population which is normally distributed, but we can say that this procedure is robust to violations of this assumption. You just find a citation if you find that this is true in your own research study. These tests are robust to violations of normality. You have to say that the sample is simple random sample. We can't always know that, but that's the assumption, that each of these scores are independent of each other. You can't be in one category. You can't be in both male and female, or in the 18 to 20 something and the 30 to something categories. and that we have at least 2 categories for each outcome, and that they should be balanced and have equal groups, but that also is sometimes violated. Okay, so we have our outcome variable, our dependent variable, and then we have one independent variable and the second independent variable. So this one's age and this one's gender. And then we have our value labels. That's how you set up the data. So using the data we've entered, we use the two-way ANOVA to test if there's an interaction effect first, and then effect for gender for the row and for the age bracket column. We use alpha is equal to 0.05. We have 2 hypotheses. First, that there is no interaction effect, then that there is no main effect. Okay, so when we do that, first we're going to check normality. We're going to do this same old thing. We're going to run it in Explorer. We'll put pulse rate here, and we'll put both of the variables into the factor list. We have to check. We're going to get 2 separate ones. One for the first variable, one for the second. We can see that none of them are significant, so we have normally distributed data across all our levels of both factors. Okay. Then we go to analyze general linear model. Careful you don't check this one, generalized linear models. That's something different. We click univariate. We move over our variables. We have our pulse rate as our DV and age group and gender. First we're going to do plots. Then we're going to do post hoc test. Then we're going to do options. All right, so we go to plots, and here we have to think a little bit. Which would we like to see separate lines for? So we have age group and gender, we have horizontal axis and separate lines. The age groups are the genders. Would I want to see a separate line for age group or gender? I would think gender, so I put that in the separate lines box and put the age group along the horizontal axis. So I move age group to horizontal axis, gender to separate lines, then I have to click add. And what that does is it multiplies these. Right? I'm just showing you where to look, but you don't have to do anything here. You click add, and then you'll see this, and this is testing the interaction effect. Then we click continue. All right, then we go to the post hoc. Our second one was to go to post hoc. Our only variable with more than 2 groups is age group, because gender only has 2, so if there's a difference, we know it's between male and female, and then we just have to look at the mean difference to see who's higher. But we don't know with age group because we have 3 groups. So here I'm going to check Bonferroni. We'll see what happens. And then I click continue. All right, then we have to go back and we do options, and we're going to click descriptives, estimates of effect size, and homogeneity tests, which is the Levines. Then we click continue, and then we go back and we say okay. So we're looking at our descriptives, and you can see we have age group and gender. This is the between subjects factor. It's just telling us our sample size and how many were there. And then you see that our trends, it looks like the young women in every category have higher pulse rates than the men. So we have female, male, and total in this age bracket, female, male, and total in that age bracket, and so forth. We can see that the women have higher pulse rates than the men in each of the age brackets. But are they significantly different? Meaning, would we have done this by chance, or is it a real thing? So let's check our assumptions. We look at our Levine's test, and we can see based on mean that we don't have equal variances. We are less than 0.05. But we could say in our write-up, based on the trend mean, or based on the median, or based on the median and the adjusted degrees of freedom. And it's just up to our reader to see if they accept that or not. And but in light of this, especially for the homework, we just want to keep going. Even if you have no equal variances, state it and keep going. So the first thing we want to do is we want to check the interaction, right? We want to see if there is an interaction between age group and gender. And here we have to be careful that we don't look at this partial eta squared. That is the effect size. And I will sometimes go here and go, oh, look, significance. But that's not it. It's the significance level here. So just remember not to do that. I do that all the time. So I go here and I look at age group times gender. That is our interaction effect. Slide across. Not significant. So that means that there is no significance. So we can move to the main effects and analyze them each one at a time. Is there a difference in age group? Is there a difference in gender? If the interaction effect is significant, then you stop there, because that would mean that it depends on which group you were in for the significant effects. So, and then I say caution about the last column. So what I mean by that is if there is a significant effect, it depends on if you're male or female, whether or not your age group there's a difference in age group, or it would be whether or not there's a difference in age group, or difference in gender, whether or not you were in different age groups. And so you can't go further. Once you've got a significant interaction, that's where you stop. But we don't have that, so we're going to analyze and look at the rest. So the next thing we do is we look at age group, and we see, no, there is no difference in age group. And there is no significant difference in pulse rates by age bracket. Namely, pulse rates are the same regardless of age. And then we look at gender and we say, oh yes, what we saw in the descriptive statistics is actually significantly different. So we can say that there is a difference in pulse rates by gender, namely that pulse rates are not the same for males and females, holding age constant, or what we say controlling for age. So if we don't consider age, we hold that constant, gender is different. And then multiple comparisons, LSD, Bonferroni, whatever it is, we use Bonferroni here. Given that the age group was not significant main effect, it really doesn't make sense to evaluate these. This is the only group, this is the only variable that had more than 2 groups, and that one wasn't significant. But sometimes they will be significant, even if the main effect is not. We're going to go with the main effect. If it's not significant, we'll stop there. So let's write up the results. First, I kind of talk about the omnibus test. A two-way ANOVA was conducted to examine the effects of gender and age group on pulse rates. Normality was assessed, and I could say established, using Shapiro-Wilkes normality tests for each cell of the design. And you don't need to report the actual statistics for Shapiro-Wilkes or for Levine's. We just want to know that you checked it and that you know what you're talking about, essentially. So you don't really need to get into the weeds with Shapiro-Wilkes and Levine's. You just say that you checked it and that you can vouch for it. So normality was assessed and established using Shapiro-Wilkes normality tests for each cell of the design, and homogeneity of variances was assessed by the Levine's test using the sum means. Now remember, Levine's was significant, therefore it was not homogeneity of variances. There was not that, but we found it when we looked at the sum means, which is why I put that here. Had it been not significant, I would have just said was assessed by using the Levine's test. That's it. Boom. Okay, then we go to the interaction effect. The interaction between gender and age group on pulse rates was not significant, and that's why I have this box here, the degrees of freedom between and the degrees of freedom error. So in a one-way analysis of variance, you do between and within, but when we're looking at these multiple comparisons, we have the degrees of freedom. So we're looking at, let me look at this one. We have 2, 54, 9.39, 0.397. So let's go to our 2 of 54, 939, p is equal to 39, partial eta squared is 0.03. Therefore, so if we had a significant interaction, we'd stop here. We didn't, so we're going to keep going. Therefore, an analysis of simple main effects for age group and gender was examined. There was not a statistically significant difference in mean pulse rates by age group, which we found was f of 2 of 54, 1.82, p is 1.173, partial eta squared, but there is for gender, and I report that out. This suggests that the pulse rates are the same across age group, but not across gender. That's a lot, but you can, when you're doing your own analysis of variance or factorial analysis, just copy this and then fill in the numbers that correspond with your problem, with your project. Okay,